An entire galaxy travels through space with no neighbors for millions of light years. These cosmic wanderers are the strangers in the void, solitary islands of stars whose very existence defies our basic ideas of how the universe is built. By the end of this journey, you will understand how these lonely giants are forcing scientists to rewrite the rules of cosmic evolution. We will investigate how a galaxy can form in total emptiness and what its undisturbed nature can reveal about the invisible dark matter shaping our reality. What does true solitude on a cosmic scale feel like to you? Our universe is not a random scattering of stars and galaxies. It possesses an architecture, a grand design on the largest scales imaginable. Picture, if you will, the cosmos not as a simple void, but as a colossal web. This is the cosmic web, a vast network of dark matter and luminous gas woven into long, winding filaments. At the intersections of these filaments, matter pools into dense clusters, home to thousands of galaxies bound together by gravity. These are the bustling cities of the cosmos. But between these brilliant strands and nodes lie the voids. These are the true deserts of space, unimaginably vast regions of near-total emptiness that can stretch for hundreds of millions of light years. In this cosmic context, galaxies are almost always social creatures. They live in groups, clusters, and superclusters, their fates intertwined with their neighbors. This is the expected structure of our universe, a pattern predicted by our best models of the Big Bang and confirmed by decades of observation, the work of astronomers like J. Richard Gott helped map this vast cosmic anatomy, revealing a universe that is far from uniform. It is within this established framework of community and connection that the strangers in the void become so profoundly puzzling. How can a single, massive galaxy come to exist in the heart of a void, separated from the cosmic web by millions of light years of nothingness? Its very presence challenges our understanding of the primordial universe. The initial distribution of matter after the Big Bang should not have easily allowed for such isolated giants to form. Finding one is like discovering a sprawling, modern metropolis built entirely alone in the middle of the Sahara Desert, with no connecting roads, no trade routes, and no explanation for how it came to be there. This foundational oddity is what makes these lone wanderers so compelling. They are not just rare, they are cosmic contradictions. So what exactly qualifies a galaxy as one of these cosmic strangers? The definition is surprisingly strict. A galaxy on the outskirts of a celestial city with its bright lights still faintly visible is merely a suburb. True isolation is far more extreme. For a galaxy to earn the title of a stranger in the void, it must exist in a region of exceptionally low galactic density, a profound emptiness far from the gravitational pull of any major cluster or group. Astronomers like Dr. Elena Dong here, who studies what are known as field galaxies, help define these parameters. The key is a lack of neighbors within a truly significant volume of space. We are not talking about a few million light years of separation, but a staggering emptiness that can span hundreds of millions of light years in every direction. These galaxies are not on the edge of the cosmic web. They are adrift in its deepest voids, the largest and emptiest structures in the entire universe. This level of solitude has a profound consequence. It means their evolution has likely been untouched by galactic collisions or close encounters for billions of years. They are pristine time capsules, offering us a rare glimpse into galaxy formation in its purest, most undisturbed form. Understanding this rigorous definition is the first step in our search, as we begin to catalogue these mysterious and solitary wanderers. The first hints emerged not from a single telescope's gaze, but from a monumental effort to map the heavens. The Sloan Digital Sky Survey began its work in the year 2000, aiming to create the most comprehensive three-dimensional map of the universe ever attempted. As its data poured in, astronomers sifting through the digital star charts began to notice anomalies. There were galaxies whose plotted positions seemed almost like errors, isolated points marooned in the vast, blank spaces on the cosmic map. Their measured redshifts placed them at immense distances, yet at those specific coordinates in the void, no other galactic neighbors were found. The initial reaction was one of profound doubt. Were these simply measurement mistakes, a trick of the light? Perhaps they were much closer or farther away than their spectra suggested, creating an illusion of solitude. It took meticulous follow-up observations confirming their distances and their profound isolation to silence the skepticism. These were not mapping errors. They were the first confirmed void galaxies, real islands adrift in an ocean of nothing. This pivotal moment marked a quiet revolution in astronomy. It forced us to acknowledge that the cosmos was not only built of brilliant cities and towns, but also contained genuine hermits, solitary giants whose existence demanded a new explanation. The scale of these cosmic voids is almost impossible to grasp. Picture a bubble so large that its emptiness could swallow thousands of galaxy clusters whole, a sphere of near-nothingness stretching for hundreds of millions of light-years. These are not mere gaps between stars, but the dominant structures of our universe, vast regions where the cosmic web has failed to weave its luminous threads. One of the most famous is the Boötes Void, a colossal emptiness that, if our Milky Way sat at its center, we would see no other galaxies in our night sky. It is a realm of profound darkness, yet it is not completely barren. The void holds secrets, including a sparse scattering of isolated galaxies, and, most importantly, the invisible gravitational scaffolding of dark matter. This unseen structure is what cosmologists like Laura Mersini-Houghton study, proposing that these voids are not static, empty holes. They are dynamic entities, expanding faster than the denser universe around them, their gravitational pull actively shaping the fate of the few galaxies that call them home. Imagine a single tree standing on an endless, barren plain. Its growth is not influenced by a dense forest, but by the unique conditions of the plain itself, the quality of the soil, and the relentless, unimpeded wind. In the same way, a galaxy adrift in a void evolves in solitude, its story written not by its neighbors, but by the vast, empty space that surrounds it. To understand the stranger in the void, we must first comprehend the profound nature of its silent, expanding home. The silent, expanding voids were no longer just theoretical spaces on a map. They now held confirmed residents, and a new question emerged. What were these cosmic loners actually like? The initial hunt for them was revolutionized by a new generation of eyes on the sky. Space telescopes like Hubble, free from the distortion of Earth's atmosphere, could peer into the deepest voids with stunning clarity, resolving the faint, delicate structures of these isolated islands. Ground-based observatories equipped with powerful spectrographs then dissected their light, revealing their secrets. This was no longer just about pinpointing a galaxy's location. It was about taking its cosmic fingerprints, measuring its mass, its rate of star birth, and the specific elements forged within its stars. One mission, the Galaxy Evolution Explorer, or GALEX, provided a stunning revelation. It observed the ultraviolet light that is a telltale signature of hot, young stars. In the quiet of the void, far from the gravitational turmoil of clusters, many of these galaxies were bursting with stellar nurseries, forming new suns at a pace that often outpaced their cousins in the crowded cosmic cities. This was a profound shift in understanding. These strangers were not just rare, they were fundamentally different. Their solitude was not a dormant state. It was an active, defining condition that shaped their very nature. The technology did not just find more of them. It revealed that we were looking at a unique class of object, living a life entirely its own, governed by the rules of the empty deep. DDO 190 drifts through the void, a faint smudge of light almost lost in the cosmic dark. This dwarf irregular galaxy, a neighbor to our own local group yet profoundly alone, embodies the concept of a true stranger. Its isolation is so complete that its evolution has been one of profound quiet. Unlike galaxies in crowded clusters, which are constantly reshaped by close encounters, DDO 190 has likely never experienced a major merger in its entire long history. The evidence for this undisturbed life is written in the light of its stars. They are predominantly old, and the galaxy possesses what astronomers call low metallicity. This is a scientific term that simply means its gas and stars contain very few elements heavier than hydrogen and helium. In the cosmic cycle, these heavy elements are forged in the hearts of stars and scattered into space by violent supernova explosions, enriching the galactic gas from which the next generation of stars will form. A galaxy that has never collided with another misses out on this cosmic recycling program. It is like a remote village that has never engaged in trade with the outside world, still using the same simple, ancient tools. Its resources remain pristine and unchanged, the work of astronomers like Igor Karashentsev, who has meticulously catalogued such isolated dwarfs, reveals them to be pristine relics. They are cosmic time capsules, preserving conditions that are remarkably similar to those in the infant universe, before galaxies began their grand, gravitational dances. By studying DDO 190, we are not just looking at a lonely galaxy. We are peering back into a quieter, more primordial time, observing how a small galaxy evolves when it is left entirely to its own devices for billions of years. The pristine solitude of a galaxy like DDO 190 points directly to a deeper, more fundamental mystery. How did it get there in the first place? Our standard picture of cosmic evolution seems to leave no room for such a solitary giant. According to the prevailing model, galaxies are born from the gravitational collapse of gas within dense halos of dark matter, structures that naturally form at the busy intersections of the cosmic web's filaments. So how could a full-fledged galaxy possibly assemble itself in the middle of a cosmic desert, a region famously devoid of the very raw materials needed for such construction? It is a contradiction that strikes at the heart of cosmology. One compelling theory, championed by researchers like Rien van der Weygaert, proposes that the voids themselves are not perfectly empty. In the primordial soup of the early universe, even the deepest void contained tiny, random ripples in the density of matter. In the expanding emptiness of a void, these minor fluctuations could have been dramatically amplified. Think of a small hill on an otherwise vast flat plain. With no other competing terrain, that single hill becomes the dominant feature of the entire landscape. In a similar way, a small, initial overdensity in the void could have gathered just enough dark matter around it to create a gravitational well, a tiny pit that slowly, over billions of years, pulled in the sparse surrounding gas until it finally collapsed to form a single, isolated galaxy. This would be a galaxy born in place, a native to the void. An alternative, more dramatic idea suggests that some of these galaxies are not natives at all, but rather cosmic exiles. They could be backsplash galaxies, objects that were once part of a bustling cluster but were flung out into the void during a violent gravitational interaction long ago. This would be like a piece of a metropolis being catapulted into the deep desert by an ancient cataclysm. However, the undisturbed, often pristine state of many void galaxies, with their quiet histories and lack of telltale damage, argues strongly against such a turbulent past. They appear too peaceful to be refugees. This leaves us with a tantalizing puzzle. The very mechanism that gave birth to these cosmic strangers in their empty realms remains one of the most active and debated questions in astronomy, a mystery written in the isolated light of a galaxy that simply should not be. This solitude, it turns out, is not a dormant state. The most startling discovery about these cosmic loners was their vibrant inner life. Logic suggested that a galaxy marooned in a void, cut off from the fresh streams of gas flowing along the cosmic web, should be a quiet, fading place. Astronomers expected to find them red and dead, populated by aging, cool stars with no new suns being born. But the data told a completely different story. Many of these isolated giants shone with a distinct, youthful blue hue, the unmistakable signature of hot, massive, and therefore young stars. They were not dying. They were thriving. How could this be? The Herschel Space Observatory provided a crucial clue. Peering into the cold, dark realms of these galaxies, it found that they held vast, unexpected reservoirs of cold molecular gas, the very raw material from which stars are built. This was the cosmic equivalent of discovering a lush, green oasis in the heart of a desert, fed by a secret, underground aquifer. In the frantic environment of a galaxy cluster, this precious gas is often violently stripped away by ram pressure as the galaxy moves at high speed through the hot intergalactic medium, or it is consumed in brief, intense bursts triggered by collisions. But in the profound quiet of the void, a different story unfolds. Here, gas can slowly and steadily accumulate, undisturbed by external forces. It is a gentle, continuous process, like a quiet rain feeding a deep, isolated lake over eons. Without the gravitational turmoil of neighbors, this gas can settle and cool, creating the perfect conditions for a long, sustained period of star formation. This revelation forced a complete rethink of what it means for a galaxy to be alive. Vitality does not always come from collision and chaos. Sometimes it is the product of profound peace, a testament to the fact that in the cosmic deep, solitude can be the very thing that nurtures life. This pristine isolation offers a unique window into the universe's most elusive component, dark matter. We know that galaxies are not just collections of stars, they are embedded within vast, invisible spheres of this mysterious substance, a gravitational scaffold that holds everything together. In the crowded galactic cities, these dark matter halos are constantly disturbed. Galaxies swing past one another, their gravitational pulls stretching and stripping these invisible envelopes, leaving them misshapen and difficult to study. But in the deep quiet of the void, a galaxy's dark matter halo can remain perfectly intact. It is like comparing a stone worn smooth by a rushing river to one found in a secluded, dry canyon, its original form preserved for eons. Cosmologists running sophisticated supercomputer simulations, such as the work led by Mark Vogelsberger, have shown that the dark matter halos surrounding void galaxies are often more pristine and more centrally concentrated than those of their cluster-dwelling cousins. This fundamental difference in their invisible architecture has direct, observable consequences. It influences how the galaxy rotates, the way it slowly draws in fresh gas from the void over billions of years. Even its long-term stability, because these solitary giants have evolved in peace, their dark matter halos are not contaminated by the gravitational chaos of a busy environment. This makes them ideal natural laboratories. When we measure the rotation of a void galaxy, we are essentially measuring the pure gravitational footprint of its dark matter, with far fewer complicating factors. These strangers in the void, therefore, may hold the cleanest, most unambiguous clues about the true nature of dark matter itself. They are not just islands of stars, they are keepers of the cosmic skeleton, their profound solitude allowing us to see the invisible framework of our universe with a clarity impossible anywhere else. The void is home to more than one kind of solitary wanderer. Among the sparse population of these cosmic deserts, we find two distinct classes of island universes, each telling a different story about life in the emptiness. On one hand, there are the isolated dwarf galaxies, the quiet, unassuming hermits of the void. They are small, faint, and incredibly common in these vast regions, representing what many astronomers consider the standard, expected outcome of structure formation in such a barren environment. Their existence fits our basic models. Then, on the other hand, there are the isolated giants. These are the true anomalies, the cosmic contradictions that defy all expectation. Consider the galaxy known as MCG plus 01020015. It has earned the Sommer title of the loneliest galaxy in the universe. This is no small, faint dwarf. It is a massive spiral, a grand island of billions of stars, yet it drifts in a region of space so profoundly empty that its nearest galactic neighbor is over 1 million light-years away. How can such a colossal structure possibly exist here? The raw materials required to build a galaxy of this scale are immense. In the sparse environment of a void, such a concentration of gas and dark matter should simply not have been possible. Its very presence suggests that the universe, under exceptionally rare and specific conditions, can somehow concentrate its resources, igniting a beacon of light in the absolute darkest corner of the cosmos. The existence of these giants forces us to reconsider the limits of galaxy formation. They are not built by the standard, efficient processes of the cosmic web. They must be the result of a cosmic fluke, a statistical outlier where a random density fluctuation in the primordial universe was just large enough and just lucky enough to gather an entire galaxy's worth of mass before the void around it expanded into nothingness. Comparing these two populations is like comparing a solitary tree on a prairie to an entire forest that somehow grew in the middle of a salt flat. One is a testament to quiet, modest survival. The other is a glorious, inexplicable mystery. The dwarfs show us the rule of void life, while the giants show us the spectacular exception, proving that even in the deepest emptiness, the cosmos can still surprise us with its capacity for creation. Its fuel source remained a cosmic puzzle. How could these isolated galaxies, so far from the cosmic web's dense rivers of gas, continue to forge new stars for billions of years? The answer appears to lie in a phenomenon known as cold flow accretion. Picture the cosmic web not as a network of brilliant superhighways, but as a system of tiny, winding backroads and hidden footpaths. Even in the vast deserts of the voids, faint tendrils of this web extend. These are not the massive, dense filaments feeding galaxy clusters, but incredibly subtle, thread-like streams of cold, primordial gas. Unlike the hot gas that dominates clusters, this cold gas does not need immense pressure to collapse. It can flow silently and directly into the gravitational embrace of a void galaxy's dark matter halo, seeping in like a slow, steady drip of cosmic fuel. This process was thought to be dominant only in the chaotic early universe, but new evidence suggests it might still be operating in the quiet of the void. Because these galaxies are so undisturbed, there is no galactic traffic to disrupt these delicate streams. no violent collisions to heat the gas, no nearby giants to steal the fuel. It is a gentle, continuous trickle, just enough to sustain a low level of star formation over eons. This discovery completely reframes the void. It is not a sterile, static emptiness. It is a landscape with its own hidden hydrology, where galaxies can tap into secret aquifers of cold gas. This subtle, ongoing nourishment explains the unexpected vitality of these cosmic loners, adding a profound new layer to our understanding of how a galaxy can thrive in the deepest solitude. This profound solitude might hold the key to a much larger cosmic conflict. One of the most pressing mysteries in modern cosmology is known as the Hubble tension. It is a stubborn and significant disagreement between the two primary methods we use to measure how fast the universe is expanding. One method, using the ancient light from the Big Bang, gives one value. The other, based on observing stars and galaxies in our relatively recent cosmic neighborhood, consistently gives a faster, different rate. This is not a small error margin. It is a fundamental discrepancy that suggests we might be misunderstanding something crucial about the physics of the cosmos. A compelling solution proposed by cosmologists like Benjamin Wandelt places our own Milky Way at the heart of the mystery. What if we are not in an average part of the universe? What if our entire galactic neighborhood resides inside a vast local underdensity, a giant bubble of relatively empty space? Think of it this way: if you are trying to measure the average incline of a vast, rolling landscape, but your measuring post was planted at the bottom of a deep, wide valley, your local reading would be skewed. You would not be getting the true, large-scale slope of the land. In the same way, if we are living inside a colossal void, our local measurement of the universe's expansion could be thrown off. The gravitational lack of mass in our surrounding void would subtly alter the apparent speed at which nearby galaxies are receding from us. This is where the strangers in the void become absolutely essential. By meticulously mapping the true distribution and properties of galaxies in the largest cosmic voids, we can test this radical idea. These solitary giants are the markers that define the emptiness. Their precise distances and motions provide the hard data needed to confirm or deny whether we are, in fact, living in a cosmic bubble. This connection elevates their study from a fascinating curiosity to a central pillar of cosmological inquiry. Understanding these lonely wanderers is no longer just about their own strange lives. It is about using their profound isolation to calibrate our entire view of the cosmos, potentially resolving a conflict that threatens to rewrite the final chapters of our universe's story. These immense digital universes are more than just video games for scientists. They are controlled laboratories for cosmic evolution, built on millions of lines of code that encode the known laws of physics. The goal of projects like Illustris-TNG is breathtakingly ambitious: to start with a near-uniform soup of dark matter and gas, mimicking the conditions just after the Big Bang, and then press play. The simulation runs for billions of virtual years, allowing gravity to work its magic, pulling matter into the filaments, nodes, and voids of a familiar-looking cosmic web. Within these sprawling digital realms, cosmologists can then go hunting. They apply the same strict definitions of isolation used by observers, scanning the virtual voids to pinpoint their solitary galaxies. The results are both confirming and illuminating. The simulations show that yes, void galaxies can indeed be born in place. They form from those rare, initial ripples in the density of matter, fluctuations that were just high enough to overcome the expansion of the void and collapse into a single, isolated island of stars. This digital genesis validates a key part of our theory, but the simulations go further, offering detailed predictions about what these cosmic loners should look like. They tell us that a true void galaxy, having never experienced the enriching mergers of a crowded cluster, should possess an older population of stars. Its overall metallicity, the abundance of elements heavier than hydrogen and helium, should be significantly lower, and without the gravitational sculpting of neighbors, its structure is often less refined. You are far less likely to find a majestic, symmetrical spiral in the void. Instead, simulations predict a higher prevalence of irregular shapes, messy and asymmetrical, or lenticular galaxies, which are like faded spiral disks that have lost their defining arms. This is the portrait of a galaxy that grew up without external influence, its form dictated solely by its own internal dynamics. The true power of this digital laboratory emerges when we hold its predictions up against the light of real telescopes. When astronomers point their instruments at a galaxy like DDO 190, they find exactly what the simulations foretold: old stars, low metallicity, and an irregular form. This agreement is a powerful vote of confidence in our underlying model of the universe, the lambda-cold dark matter model. It shows that this framework, for all its mysteries, can accurately reproduce even the most extreme outliers of cosmic structure. By simulating Solitude, we not only explain the existence of these strangers, but also reinforce the very rules we believe govern the cosmos. This profound piece leaves a lasting signature on the very shape of a void galaxy. In the densely packed galactic cities, the architecture is often brutal and uniform. Galaxies are frequently stripped of their delicate features, transformed by relentless collisions into smooth, featureless ellipticals, their stellar populations jumbled into a chaotic ball. This is the established rule known as the morphology density relation. The denser the environment, the more likely a galaxy is to lose its elegant structure. But in the silent expanse of the void, this rule is completely rewritten. Here, galaxies are not sculpted by external forces. They are left to grow according to their own internal rhythms. The result is a population dominated by late-type spirals and irregulars. These are the galaxies that have never been disturbed. Their spiral arms are not the bold, sweeping arcs you see in textbooks. Instead, they are loose and flocculent, like tufts of cotton or clouds of smoke, a testament to a gentle, unorchestrated evolution. They lack the grand design structure that can be tidally induced by a close gravitational encounter with a neighbor. A grand design spiral is a galaxy that has been touched, its shape influenced by another. A void spiral is a galaxy that has always been alone, its form a pure expression of its own slow, internal dance of stars and gas. This is the clearest possible imprint of a lonely history. The morphology of these cosmic strangers is not just a classification. It is a storybook, and its pages tell a tale of billions of years spent in perfect, undisturbed solitude. That central mystery remains unresolved. Are these cosmic loners true natives of the void, or are they exiles from the bustling galactic cities? This is the fundamental question driving astronomers today, and the evidence points in two compelling yet contradictory directions. The first and most favored idea is the primordial origin story. This theory posits that these galaxies are genuine natives, born in the emptiness from the very beginning. The strongest support for this comes from their pristine physical condition. Many void galaxies display beautifully undisturbed disks and irregular shapes, showing no scars from violent gravitational encounters. They are like ancient trees in a secluded valley, their rings telling a story of uninterrupted growth, never bent or broken by a passing storm. Furthermore, our most advanced cosmological simulations confirm that it is statistically possible, though rare, for a random density fluctuation in the primordial void to gather just enough dark matter to seed a single galaxy. They are the cosmic equivalent of a settlement that sprung up from a lone, isolated well, rather than a town built at a major crossroads. The alternative, more dramatic theory is the ejection hypothesis. This suggests that some of these galaxies are not natives at all, but rather refugees. They could have been born in a cluster and then violently flung out into the void by a gravitational slingshot effect, often involving a supermassive black hole interaction. This would create a hypervelocity galaxy, a cosmic castaway hurtling through the emptiness. While this is a compelling story for a handful of peculiar cases, it fails to explain the majority of void dwellers. A galaxy that suffered such a traumatic ejection would bear the marks of that violence. Its disk would likely be warped or disrupted, and its journey through the dense intercluster medium would have stripped away its delicate gas reserves. Yet, so many of the galaxies we find in the voids are gas-rich and structurally serene, their peace speaking against a turbulent past. So how do we settle this cosmic debate? The answer lies in reading the galaxy's own life history, written in the light of its stars. Astronomers act as cosmic detectives, using powerful telescopes to gather two key pieces of evidence: the galaxy's trajectory through space and the precise ages of its stellar population. A galaxy with a trajectory that points directly back to a nearby cluster is a strong candidate for an exile. More tellingly, a galaxy whose stars are all remarkably old, with no signs of multiple, collision-induced bursts of star formation, powerfully argues for a primordial origin. It is a galaxy that has been left to its own devices for its entire existence, a genuine stranger born in the quiet of the void, its solitude not an accident of fate, but its original defining state. This chemical purity is a direct consequence of their lonely existence. The gas inside a void galaxy tells a story of self-sufficiency, untouched by the intergalactic commerce that defines more crowded regions. In a bustling galactic cluster, the space between galaxies is not a perfect vacuum. It is filled with a hot, diffuse medium that has been heavily polluted over billions of years. When massive stars live fast and die in supernova explosions, they blast newly forged heavy elements, what astronomers call metals, out into their surroundings. In a cluster, these enriched winds from countless galaxies mix together, creating a shared, metal-rich intergalactic environment. Any galaxy moving through this space is constantly bathed in this recycled, polluted gas. It is like a city whose atmosphere is filled with the industrial smoke of its neighbors. But in the deep void, there are no neighbors to contribute. A galaxy's gas reservoir is a closed system, an isolated pond that receives no inflow from other streams. When a star goes supernova in a void galaxy, the heavy elements it ejects fall back into the same galactic pool. There is no vast intergalactic medium to dilute them, and no fresh, unpolluted gas from outside to mix in and lower the overall concentration. The result is a very slow, internally driven process of chemical enrichment. Astronomers measure this by analyzing the galaxy's light through a spectrograph, looking for the telltale absorption lines of elements like oxygen, carbon, and iron. In void galaxies, these lines are often strikingly weak. The metallicity, the proportion of elements heavier than hydrogen and helium, is remarkably low. This is the signature of a system that has been relying on its own resources for eons. Its gas is more pristine, closer to the primordial composition of the universe just after the Big Bang, before generations of stars had a chance to seed the cosmos with heavier elements. This makes these cosmic loners invaluable laboratories for studying the fundamental process of nucleosynthesis, the cosmic forging of elements inside stars. In a typical galaxy, untangling its chemical history is incredibly complex. How much of its metal content came from its own stars, and how much was imported from galactic neighbors through collisions or from the polluted cluster medium. It is like trying to trace the source of pollution in a river that has a dozen industrial towns along its banks, but a void galaxy is a single, isolated town with one factory. By measuring its metallicity, astronomers can piece together a much cleaner history of its star formation. They can see the direct results of its own internal stellar life and death cycles, a history that has been largely independent of outside influence. This chemical fingerprint is perhaps the most definitive proof of their profound isolation, a purity that could only be achieved through an existence of absolute solitude, far from the polluting winds of the cosmic crowd. This missing satellite problem presents a quiet crisis in our cosmic models. Our most sophisticated simulations of the universe consistently generate a specific, bustling scene around large galaxies like our own Milky Way. They predict a rich halo swarming with hundreds of small dwarf satellite galaxies, each a tiny island held in the gravitational sway of the giant. Yet when we look up at our actual skies, we find a much quieter neighborhood. We observe only a few dozen of these dwarfs, not the teeming multitudes the computers insist should be there. This glaring mismatch is the missing satellite problem, a nagging flaw that suggests something is wrong with our picture of galaxy formation, or perhaps even with our understanding of dark matter itself. But what if the problem is not with the universe's rules, but with our perspective? What if we have been looking for answers in the wrong place, inside the chaotic galactic cities, when the true solution lies in the deep silence of the voids? Intriguingly, the same simulations that create this problem in clusters show a very different story unfolding in the cosmic deserts. When a massive galaxy forms in the profound isolation of a void, it does so from a single, isolated peak in the primordial density field. There are no bustling suburbs of smaller clumps merging together to build it up. It is a solitary monarch with no nearby courtiers to gather. Because of this isolated origin, these void giants simply do not accumulate the same vast entourage of satellite dwarfs. Their gravitational domain is quieter, more sparsely populated from the very beginning. This is not just a theoretical prediction. Observational studies focusing on isolated giant galaxies within voids have confirmed this startling fact. These cosmic loners have significantly fewer satellite galaxies orbiting them than their identical counterparts living in the dense clusters. The environment is not just a backdrop. It is the decisive author of a galaxy's social life. In the crowded metropolis, a large galaxy's gravity cannibalizes and strips apart countless smaller dwarfs, while also preventing new ones from easily forming. But in the void, that same giant galaxy evolves in peace, never experiencing the violent mergers that both create and destroy a satellite population. This discovery transforms the void from a mere curiosity into a vital laboratory. By studying these isolated systems, we can isolate the variable of environment. We can see what happens to galaxy formation when it is stripped of all the complex, messy interactions that define life in a cluster. The missing satellite problem appears less severe in the void because the conditions for it were never there to begin with. This gives cosmologists a clean test case. If our models can accurately predict the sparse satellite populations around void giants, then we are on the right track. The problem may not be with the core physics, but with our ability to simulate the violent, complicated history of galactic cities. These strangers in the void, in their profound solitude, are helping us debug the universe, offering a clearer view of the rules that govern all galaxies, from the loneliest giant to our own crowded home. A galaxy's environment is its ultimate sculptor, and the void is the most patient and gentle master of all. In the dense, violent cores of galaxy clusters, evolution is a brutal affair. Galaxies are wrenched out of shape by the gravitational pull of their neighbors, a process known as galactic harassment. Their lifeblood of cold gas is violently stripped away as they plow through the searing hot intergalactic medium, a phenomenon called ram pressure stripping. Their trajectories are chaotic, their structures shattered by collisions, but in the deep quiet of the void, none of this happens. Here, a galaxy is left entirely alone. There are no close encounters to warp its disk, no hot wind to blow away its star-forming fuel. The evolution it undergoes is passive, a slow and steady unfolding dictated solely by its own internal physics. This profound difference means the star formation history of a void galaxy reads not like a series of explosive bursts, but like a long, gentle curve. In a cluster, a galaxy's star formation is often punctuated by sharp, intense peaks, brief, brilliant fires lit by a merger with another galaxy. But a void galaxy has never known such violence. Its stars are born in a continuous, quiet drizzle over billions of years, a testament to a stable and uninterrupted supply of cold gas. Its dark matter halo, the invisible gravitational anchor that holds it all together, remains perfectly intact. Unlike its cluster-dwelling cousins, whose halos are constantly peeled away by tidal forces, a void galaxy's halo retains its original mass and pristine, spherical shape. This gentle, unperturbed existence makes these cosmic loners something incredibly valuable, a benchmark. They show us what a galaxy looks like when it is left entirely to its own devices. By studying them, we can see the baseline, the default state of galactic evolution, free from the dramatic, complicating interference of a crowded environment. To truly understand the life story of any galaxy, from our own Milky Way to the most distant island in the sky, we must first comprehend the quiet, profound influence of the empty deep. The silent history of these cosmic loners is about to be read with unprecedented clarity. A new era of discovery is dawning, driven by observatories so powerful they will transform our view of the void. The James Webb Space Telescope, with its profound sensitivity to infrared light, acts as a cosmic time machine. It can cut through the dust and gas that obscures our view, peering directly into the stellar nurseries and ancient hearts of void galaxies. This is not just about seeing them more clearly, it is about dissecting their life story. Webb will analyze the light from their oldest stars, determining their precise age and composition, telling us definitively if these galaxies are truly primordial relics. It will reveal the faintest, most delicate structures within them, features too dim for any previous telescope to see, showing us the unblemished architecture of a galaxy that has never been touched. While Webb studies individual galaxies in stunning detail, another colossal project will capture the big picture, the Vera C. Rubin Observatory is embarking on a decade-long mission called the Legacy Survey of Space and Time. This will be the most ambitious movie of the universe ever made, scanning the entire southern sky night after night. Its primary gift to void hunters will be sheer numbers. It will not just find a few more isolated galaxies. It will catalog millions, mapping the cosmic voids in higher definition than ever before. This flood of data will finally provide the robust statistics we desperately need. We will move from studying fascinating oddities to understanding the entire population of void dwellers. How common are the isolated giants versus the quiet dwarfs? What is the true range of their shapes, sizes, and star formation rates? With this census, we can rigorously test the predictions of our most advanced simulations. Do the numbers of void galaxies match what the models say they should? Do their properties align with the picture of a gentle, primordial origin, or will the data reveal something entirely unexpected? This is where the real potential for revolution lies. Every time we build a telescope that can see farther and fainter, we discover a new class of object that we never knew existed. The profound darkness of the voids is the perfect hiding place for the universe's strangest secrets. We might find hyper-diffuse galaxies so ghostly they are barely there, or lone galaxies with bizarre chemical signatures that point to a formation process we have not yet dreamed of. The future of understanding these strangers is not about confirming what we already know. It is about being prepared for the moment they show us something we have never seen before, forcing our cosmic story to evolve once more. This deep solitude creates a galaxy of perfect independence, yet astronomers have uncovered a subtle cosmic choreography. Even the most isolated void galaxy is not spinning at random. Its rotation, the axis around which its stars turn, often aligns with the gravitational tides flowing from the cosmic web millions of light years away. This is a connection that defies the apparent emptiness. Imagine a single leaf floating in the center of a vast, still pond. Though no other objects are nearby, the leaf still orients itself in the current of a slow, deep underflow you cannot see. In the same way, a void galaxy responds to the large-scale structure of the universe. It feels the gentle gravitational pull from the distant, dense filaments of the cosmic web, a force that acts like a cosmic tide, ever so slightly guiding its growth and spin over billions of years. This alignment is not a product of recent interactions. It is a fossil record, a preserved memory of the galaxy's very beginning. The direction from which this ancient galaxy first began to draw in its gas and dark matter is imprinted forever in its rotational spin. It tells us the story of its birth, revealing the axis along which the primordial universe delivered the raw materials to build this solitary island. This discovery is profoundly humbling. It means that no galaxy, no matter how alone it appears, is ever truly disconnected from the cosmic whole. Even the ultimate stranger in the void is still dancing, slowly and gracefully, to the silent, universe-wide music of gravity. This profound isolation does more than just preserve a galaxy's history. It challenges the very laws we believe govern the cosmos. The peculiar properties of void galaxies, especially their pristine rotation and the behavior of their stars, have led some physicists to propose a radical idea. What if our understanding of gravity itself is incomplete? One prominent alternative is known as modified Newtonian dynamics, or MUND. This theory suggests that the effects we attribute to dark matter are not caused by an invisible substance at all. Instead, they are the result of gravity behaving differently at extremely low accelerations, the kind of gentle pulls that dominate in the near-empty vastness of a void. In this view, a galaxy's rotation is not governed by an unseen halo of dark matter, but by a subtle modification to Newton's famous laws. The pristine conditions of a void galaxy create the perfect laboratory to test this idea. In a crowded cluster, a galaxy's motion is a chaotic mess, influenced by the gravitational pull of countless neighbors and the violent processes of ram pressure and harassment. It is nearly impossible to isolate the pure signal of gravity's pull, but in the void, a galaxy spins in perfect quiet. Its rotation is dictated solely by its own visible mass and the underlying force of gravity, with no environmental noise to confuse the measurement. This makes a void galaxy the ultimate controlled experiment. If MUND is correct, the rotation curves of these isolated giants should follow a very specific and predictable pattern that differs from the predictions of the standard dark matter model. Every precise measurement of a void galaxy's spin is therefore a direct test of our most fundamental cosmic rules. While the prevailing lambda-cold dark matter model still provides the best overall fit for the universe's large-scale structure, these cosmic loners offer a unique chance to probe for cracks in the foundation. A single, well-measured void galaxy with rotation that stubbornly defies both models could be the clue that leads us to an entirely new understanding of physics. The strangers in the void are no longer just subjects of curiosity. They have become the arbiters in a grand debate, their silent solitude holding the potential to confirm our deepest theories or force us to rewrite the rules of the cosmos. Our own existence may be intertwined with the cosmic architecture we observe. This line of thinking leads directly to the anthropic principle, a profound and sometimes controversial idea in cosmology. It suggests that the universe we can observe must have properties that allow for the emergence of conscious life to observe it. In essence, the universe is the way it is, at least in part because we are here to see it. Now apply this to the strangers in the void. Their existence proves that the cosmos is capable of producing wildly different environments, from the densely packed galactic cities to the deepest, loneliest deserts. This variation forces a deeply personal question. What if our own Milky Way was not a part of the local group, but was instead a solitary giant adrift in one of these immense voids? How would that profound isolation have shaped our history and, more importantly, our very existence? The development of complex life, at least as we understand it, relies on a certain cosmic stability. In a void, our galaxy would have evolved in undisturbed peace. It might be richer in gas and brimming with young blue stars, a vibrant island in the dark. But this very solitude could have been a barrier to life. The gentle pace of evolution in a void means fewer galactic collisions. This is crucial because it is believed that the heavy elements necessary for rocky planets like Earth and for the chemistry of life itself are forged in the violent mergers and stellar explosions that are more common in crowded galactic neighborhoods. A void galaxy, with its quieter history and lower metallicity, might lack the necessary planetary building blocks. Its planetary systems could be rarer or composed of simpler, lighter elements. Furthermore, our position in a relatively dense part of the cosmic web gave us a front-row seat to the universe. The brilliant light from neighboring galaxies like Andromeda allowed early astronomers to begin mapping the cosmos, a task that would be infinitely more difficult in the absolute blackness of a void. The mere fact that we are here to ponder these lonely galaxies suggests that our place in a connected community was not an accident, but perhaps a necessity. Contemplating the strangers in the void is more than an astronomical exercise. It is a mirror held up to our own cosmic fortune, a reminder that our vibrant, connected galactic home may have been the very condition that allowed us to look out into the deep and wonder about those who are truly alone. The cosmic void holds ghosts. Among the most enigmatic of all the strangers are the ultra-diffuse galaxies, or UJ. These are spectral islands of stars so faint and spread out that they were nearly invisible to our telescopes for decades. They were first spotted in the one place we expected to find damaged and distorted objects, within the violent, dense cores of galaxy clusters. In that brutal environment, their puffed-up, ethereal forms made a kind of sense. Astronomers theorized they were once normal galaxies that had been mauled, their stars scattered by gravitational harassment and their gas stripped away, leaving behind a vast, faint ghost of their former selves. But then our surveys peered deeper into the voids and found the impossible. UDGs were there too, drifting in the profound emptiness. This discovery shattered the old story. How could a galaxy be stretched into such a diffuse, ghostly state in a place with no neighbors to harass it, no violent encounters to pull it apart? The void offers no such external forces. Its silence is absolute. This means the puffing up process must be an internal one. These void UDGs are likely born this way. One compelling theory suggests they are cosmic late bloomers, or perhaps galaxies that never truly bloomed at all. They may have assembled massive halos of dark matter early on, but for reasons we do not yet understand, their gas failed to cool and collapse efficiently. Star formation sputtered, never igniting into the brilliant firestorm that creates a classic bright galaxy. They are like vast, empty castles with only a few candles lit in their countless rooms, failed galaxies that never managed to fulfill their initial potential. Their existence in isolation forces a complete rethinking of what a galaxy can be. It shows that the recipe for galaxy formation, even when followed in the same quiet kitchen of a void, can produce wildly different outcomes, from vibrant spirals to these enormous, faint phantoms. The discovery of void UDGs dramatically expands the family of cosmic loners, proving that the emptiest places in the universe are home to a wider, weirder menagerie of objects than we ever dreamed. Their profound solitude might have once lit up the entire cosmos. To understand how, we must journey back to the universe's infancy, a time known as the epoch of reionization. After the Big Bang, the cosmos was a dark, featureless sea of neutral hydrogen gas. Then, the first stars and galaxies ignited, and their intense ultraviolet radiation began to tear apart those hydrogen atoms, stripping away their electrons and flooding the universe with light. This was reionization, the pivotal moment the cosmos turned on, transforming from an opaque fog into the transparent void we see today. The biggest question has always been what provided the immense amount of UV light required for this colossal task. The usual suspects are the dense, early clusters of galaxies, brilliant cities in the young cosmos. But what about the loners, the first strangers in the void? Their sparse numbers would seem to make them minor players, but their environment gives them a unique and powerful advantage. In a crowded galactic region, a huge amount of a galaxy's ultraviolet radiation is absorbed by the dense gas and dust of its own intergalactic neighborhood. It is like a brilliant street lamp in a dense, foggy city. Its light only travels so far before it is swallowed by the haze, but a galaxy born in an early void faces no such obstacle. Its powerful UV light would blast outwards, unimpeded, into the pristine neutral hydrogen surrounding it. With no neighboring galaxies to absorb this radiation, it could travel for millions of light years, carving out vast, transparent bubbles in the cosmic fog. While one such galaxy could only clear a local area, a population of them, scattered like distant lighthouses across the early universe, could have collectively punched holes in the darkness. Their isolated beams might have connected, merging to create the vast, transparent voids we observe today. This is a difficult hypothesis to prove, as it requires spotting these solitary galaxies at immense distances at a time when the universe was still mostly dark. The James Webb Space Telescope is now our most powerful tool for this search. By staring deep into high redshift voids, regions that correspond to this ancient era, it might finally detect the faint, lonely glows of the first void galaxies. If it finds them and finds they were bright and numerous enough, we will have to rewrite the story of cosmic dawn. These strangers, so often seen as passive relics, may have been active architects, their isolated light helping to sculpt the clear, dark expanses of the modern cosmos. The motion of stars and gas within a galaxy writes its autobiography in the language of physics. We call this kinematics, the study of internal motion, and it reveals the hidden distribution of mass, both seen and unseen. In the serene emptiness of a void, you would expect this story to be simple, a tale of a slow, steady, and undisturbed spin. Yet when astronomers point their spectrographs at these cosmic loners, they sometimes read a more complex narrative. They find galaxies with bizarre internal dances, where the central core of stars rotates in the opposite direction to the outer disk, or where the disk of gas is tilted at a strange angle compared to the disk of stars. These are not the motions of a system that has been left completely alone. A counter-rotating core or a misaligned disk is a classic signature of a past merger, a gravitational event where a smaller galaxy was swallowed whole. The ingested galaxy's unique spin and angular momentum becomes a fossilized record within the larger one, a ghostly presence that permanently twists the galaxy's internal dynamics. Discovering these features deep inside a void galaxy is like finding a lone settler in the desert who possesses a unique, foreign tool. It tells you that despite the profound solitude, a visitor once came or a package from afar was delivered. This suggests a history that is not one of perfect isolation, but of quiet, punctuated events. Perhaps a small, dark matter-dominated dwarf galaxy, itself a child of the void, drifted too close and was cannibalized billions of years ago. Or more subtly, a lone, thin filament of the cosmic web, a single thread winding through the emptiness, slowly fed a stream of cold gas into the galaxy from a specific direction over eons. This accreted gas, arriving with its own particular spin, could have gradually torqued and realigned the galactic disk. This complexity forces us to refine our idea of solitude. A void galaxy's life is not necessarily defined by total emptiness, but by a profound lack of constant company. Its history can include these rare, gentle acquisitions, these quiet mergers that leave a subtle but detectable mark without the violent, transformative chaos seen in clusters. The Kinematics reveal that even in the deepest void, a galaxy's life can be one of quiet eventfulness, a story not of absolute loneliness, but of rare and momentous encounters separated by billions of years of peace. The search for the ultimate cosmic hermit has become a grand scientific endeavor. Astronomers have turned their most powerful telescopes toward the deepest voids, competing to identify and crown the single most isolated galaxy in the observable universe. While famous loners like MCG plus 0102015 hold a Sommer title, newer, deeper surveys continuously uncover galaxies that appear even more profoundly alone. This raises a fundamental question. How do you even define the most isolated? Is it the galaxy sitting at the center of the largest possible sphere of emptiness, a perfect bubble of nothingness stretching for hundreds of millions of light years in every direction? Or is it the galaxy with the lowest possible density of neighbors within a staggering volume of space, say, 1 billion light years across? Each definition requires meticulous mapping and complex calculations, turning the hunt into a rigorous statistical exercise. But this is far more than an astronomical curiosity or a contest for a grim title. By finding these extreme outliers, these ultimate strangers, we are performing a crucial stress test on our theories of cosmic evolution. We are asking the cosmos a direct question. What is the absolute minimum density of matter, the barest trickle of environmental resources, required for gravity to ignite a single island of stars? Every new candidate, every galaxy found in a deeper, darker void than the last pushes the boundary of that limit. The quest for the loneliest galaxy is not just about finding a record holder. It is about discovering the frontier where galaxy formation itself becomes impossible, revealing the final, fundamental rule written into the fabric of our expanding universe. These hydrogen clouds racing around our own galaxy may be distant relatives of the loneliest cosmic wanderers. High-velocity clouds, or HVCs, are vast structures of neutral hydrogen gas orbiting the Milky Way at speeds that defy simple explanation. For decades, their origin has been a subject of intense debate. Are they mere shreds of galactic debris, the torn-apart remnants of ancient collisions? Or are they something far more profound, the leftover building blocks of galaxy formation itself, pristine relics from the early universe that never managed to coalesce into stars? This second possibility leads to an extraordinary idea, the concept of dark galaxies. A dark galaxy is not a void of nothingness, but a substantial island of dark matter, a gravitational anchor that gathered a halo of hydrogen gas but for some unknown reason failed to light up with the brilliant fires of star birth. It would be a ghost ship, a fully rigged vessel adrift in the cosmic ocean with no crew and no lights, its presence detectable only by the faint radio whisper of its hydrogen gas and the subtle tug of its gravity. If such entities are difficult to find near our bright, bustling Milky Way, then the deep voids are where they should truly thrive. In those expansive deserts, the conditions for efficient star formation are rarely, if ever, met. The gentle accretion of gas is often too slow, the density of the primordial material too sparse to trigger the collapse into stellar nurseries. It is the perfect environment for creating failures, for birthing dark matter halos that gather just enough gas to be detected, but never enough to shine. This is why a new generation of radio telescopes is now turning its gaze toward the deepest voids, conducting surveys that scan the emptiness not for light, but for a specific, faint signal, the 21-centimeter emission line of neutral hydrogen. This is the unique radio fingerprint of unlit primordial gas. Finding a population of these dark galaxies would be a discovery of monumental importance. It would reveal an entire hidden population within the cosmic web, a shadow universe of structures that have, until now, existed only in theory. These dark inhabitants would be the ultimate strangers in the void, the silent, invisible majority that may well outnumber the glowing galaxies we see, finally providing direct, tangible evidence for the dark matter halos that are predicted to be the true foundation of our universe's structure. These solitary giants are more than astronomical curiosities. They touch something deep within the human spirit, evoking a profound sense of awe and a chilling form of cosmic loneliness. Their existence is a powerful metaphor for isolation on a scale that defies our earthly comprehension. The late astronomer Carl Sagan masterfully used such vast perspectives to reflect on our own fragile place in the cosmos, and these void galaxies offer perhaps the ultimate example. Contemplating them forces a deeply personal question. What would life be like for a hypothetical civilization that evolved on a world within one of these islands? Their reality would be fundamentally different from our own. Their night sky would be an almost perfect, unbroken blackness, a void punctuated only by the stars of their own galaxy. There would be no Andromeda, no large Magellanic Cloud, no faint smudges of light to hint at other island universes. Their entire understanding of the cosmos would be constructed from the light of their own suns and the faint, deeply redshifted glow of the ancient cosmic web, a dim fossilized pattern on the edge of perception. Imagine a culture that never knew other galaxies existed until their technology advanced enough to detect these whispers from the void. Their cosmology would be one of profound solitude, a universe seemingly built for them and them alone. This thought experiment is not just a flight of fancy. It highlights by stark contrast how our own vibrant cosmic neighborhood has actively shaped our science and our culture. The presence of our galactic neighbors gave us our first clues that the universe was larger than the Milky Way. It inspired our maps, our myths, and our relentless drive to explore. The strangers in the void remind us that our window to the cosmos is not just a view, but a specific address, one that has fundamentally defined who we are and how we see our place in the grand scheme of everything. Our journey through the vast cosmic voids has brought us face to face with a profound truth. The universe is not only built of brilliant cities, but also of deep deserts, and within those deserts, solitary giants travel a path of their own. These strangers in the void have challenged our most fundamental ideas, forcing us to rewrite the rules of cosmic evolution. Their very existence proves that galaxy formation is possible even in the most barren environments, that the universe can, under rare and special conditions, concentrate its resources to light a single candle in an ocean of darkness. We have learned that their solitude is not a dormant state, but an active, defining condition. Shielded from the gravitational turmoil of clusters, these galaxies evolve in profound peace, their star formation a gentle, sustained drizzle over billions of years. This undisturbed existence makes them pristine time capsules, offering us the clearest possible view of the invisible dark matter that shapes them and preserving a record of the universe's initial conditions that is uncorrupted by a violent history. As we reflect on the immense, empty spaces between the threads of the cosmic web, we are reminded that even in the deepest void there is light, there is matter, and there is profound mystery. The study of these cosmic loners is far from over. With every new telescope and every deeper survey, we peer further into the darkness, knowing that the next great discovery, the next stranger in the void, may be waiting in the next patch of empty sky. What do these solitary wanderers make you wonder about our own place in the cosmos? Share your thoughts in the comments and subscribe to continue exploring the universe's greatest mysteries with us. The enigma of the void galaxies endures precisely because their existence challenges the core of our cosmological models. Every time we believe we are nearing an answer, these solitary giants present a new layer of profound complexity. They are far more than astronomical oddities. They are the ultimate test cases, the cosmic experiments that nature has been running in perfect isolation for billions of years. Their continued observation directly probes the mysterious nature of dark matter, gauging the shape and density of its invisible halos without the interference of a crowded environment. They question the very laws of gravity, asking if our rules hold true in the deepest, quietest corners of the cosmos where the pull of matter is at its absolute weakest. And they hold the most pristine record of how a nearly smooth, featureless universe after the Big Bang could possibly clump into the intricate, web-like structure we observe today. The void is not a barren wasteland. It is a universe of unanswered questions, a silent frontier where every faint point of light is a messenger. The solitary galaxies drifting within this immense darkness are not just inhabitants of the emptiness. They are the keepers of the keys, and their silent, steady light promises to unlock the final chapters of our cosmic story.